By Bruce Hayek. I guess it gives me a chance to say a few things, first of which is thanks to the organisers of this programme and this workshop. Just done a fantastic job. It's great to see so many people here. The second thing is, as usual, you know it's being recorded. Please switch off your mobile phones, because if you don't switch off your mobile phones, it will be picked up even if they're in silent mode. So do please switch them off. A few words only about Bruce. He'll be very well known to all of you, I'm sure. He's the Husk Professor at the University of Illinois at Urbana-Champaign, and we're just delighted that you're going to give this lecture. As Bruce has seen these on the web a couple of times, so he knows exactly what I'm going to say now. This is a very special timepiece. It is absolutely accurate, and it is the world standard definition of Newton hour. Because when I turn it over, that's the period for the lecture. Bruce, welcome and thank you.
Thank you. Thank you, David. I'm very happy to be here. Thank you to the organizers for inviting me to give this lecture. And so I'll be speaking about mathematical analysis of peer-to-peer communication networks. I'd like to thank my collaborators, Laurent Massoulier, Sujay Sanghavi, a former student of mine who's now at University of Texas at Austin, and Ji Zhu, who's out there somewhere. Ji, where are you? All right there. Okay. And the overview of the presentation is to give an overview of peer-to-peer communication and networks first. And I'll talk about file exchange with a fixed peer population, and then which is work with Sujay and Laurent. And then I'll be moving on to work where there's continuous arrival of peers coming into the system. There's a fluid analysis of Massoulier and Bojanovic, their paper. I'll review that, and then talk about the work that Ji and I did related to that, and then I'll close up with some discussion. Okay, so the first overview is pretty general, just about what peer-to-peer communication is. So a traditional file service, we have a single server, and then if a peer wants to download a file, the server just sends the file out. And a bottleneck would be the server, because of the sending out the packets one at a time. So in peer-to-peer file communication, a server could send out the file, and then peers can exchange the file among themselves. So the capacity scales with the number of peers. So it's a robust, scalable mechanism. It takes a lot of traffic on the internet. This is the rough composition of internet traffic today. It's taken from this study. Most of it's Africa and Europe, large part of the world covered. So the peer-to-peer file transfer, which is about half of that is movies. Software is around 20 to 30%. Games, and the mixture varies over time, is about 50 to 60% of the traffic on the internet. It's estimated at. And of course, some service providers view this as something to get rid of, and there's a lot of controversy surrounding it because of a lot of it's copyrighted material sent illegally, but there's a lot of legal uses of it. And so it's something to pay attention to because it has such a large fraction of the capacity of the internet that's being used. Web pages, including social networking like Facebook, have 20 to 30% of the traffic in the internet. Web streaming, for example, seminars like this being streamed from the website would be 8%. Voice over IP, it's an important application, but it only uses about 1% of the capacity of the internet. And then 5% for other things like news groups, emails, gaming, and other things. These things are fluctuating over time. And we know we can't always just design the internet just for one mixture of traffic because things change over time. And we could see peer-to-peer file transfer increase or decrease. It's been decreasing a bit lately because this Facebook has sort of been taking market share from it. Okay. So a first-generation peer-to-peer system would take the seed or source would take the file and send a complete file to neighbors, and then they would send the complete file on and so forth. Okay, it'd be kind of slow because you have to download the whole file before that peer could be useful. So the second generation system, you take the file and break it into pieces or chunks, and those pieces are sent to other peers, and then those peers can start immediately sending those pieces on to other peers before they get the whole file. Okay, so the peers can start serving pieces without waiting for the entire file. It's more effective for serving large files, and BitTorrent, which is the most popular peer-to-peer system, uses that. eDonkey use that. I just put one picture up here. I like this model from this paper of Zhao, Louis, and Chu, a model of peer-to-peer live streaming. The next few slides just talk about a lot of variations. There's not one peer-to-peer situation, but there's a lot of different scenarios with different models. And so our approach is to look at the different systems that are out there and then try to study 2 or 3 models that capture a lot of the dynamics, and a lot of things that go on without looking at all the details. That's the idea. And this one reminds me of a jet engine with the fuel coming in. It sort of goes in, and there's the peer-to-peer turbine mixes the packets together, and what comes out the other end is a pure stream. Okay, so in a live streaming, there's a source. Looks like a spray can coming out here. So this seed, this is piece 44 coming out. This is the play time. So you've got a bunch of peers here. The seed just sprays out these pieces to the peers, and then the peers exchange pieces as time goes on. Okay, so in the next slot, the seed sprays out piece 45, and then there's, each row here is a peer. So this peer is missing piece number 39 here. Piece 36 is being played out. They're looking at their viewers, seeing piece 36. They want to get piece 37 next, 38, because that's what's going to be coming up. On the other hand, they like to collect pieces early on because those will be useful to give to other peers. Okay, so it's good to get pieces right before the deadline, and it's also good to get pieces early because then you can give those to other peers. So anyway, I just think of this as like some lighter fluid or something, and this going here. And so it's an interesting model, and there's interesting asymptotics. They look at the density-dependent Markov process model. So there is a limit theorem there, and then you try to look at optimal policies for if one peer contacts another peer, which piece should they exchange? Should go for the last, fill in the last pieces, or get the early pieces. Another phenomenon related a little bit what I said about controversy in peer-to-peer systems is the notion of an ISP-friendly peer-to-peer protocol. So I talked to a service provider yesterday, Tim Rossiter. I don't know if he's watching me now, but as he was saying, they can throttle a lot of the traffic because they have deep packet inspection is being implemented on a lot of routers, so they can look into the packet and see what kind of a packet it is. And if it's a peer-to-peer packet, they could drop it. And so the people that write peer-to-peer software use it. Well, first of all, they try to disguise the packets. That's one thing. Encrypting it. Yes, Sergey? Okay. ISP is Internet Service Provider. Internet Service Provider. There are companies that would charge you to hook up to the internet. And then if you're a peer, then the traffic, if you're a peer and you choose other peers at random by choosing a random other peer that's got the file, much of the traffic would be crossing from one ISP over the boundary to another ISP. And the ISPs have a lot of capacity inside their network, but there's limited capacity from one ISP to a neighboring ISP, and they have to pay to use that. Okay, so it costs them a lot more in terms of the connectivity they have to the rest of the internet to have one peer settling in their ISP, downloading and then uploading to the whole rest of the world. Okay, so the ISP would rather have you have a seed download a few files into their ISP and then have all the exchange going on within the ISP as much as possible. And then if the peer-to-peer protocols work that way, they would be less of a nuisance to the ISPs and they wouldn't be throttled so much. And the ISPs may even have some incentive to help with this because there is apparently some value to this traffic going on, and the ISPs want to have happy customers. So this, and by doing this, you also end up with smaller populations. So it sort of raises the interest in understanding how the peer-to-peer system works with smaller populations because of this ISP-friendly thing. Okay, another phenomenon with BitTorrent and a lot of the file sharing is the idea of a flash crowd, where there's some file and word passes around that there's this file available, it gets advertised, and peers start downloading it. So you get a graph something like this. You might have several thousand peers downloading the file simultaneously for a few hours. This is like the first 24 hours, and then after a few hours it kind of starts going down again. This could vary by factors of 10 or 100 in how high it can go and how long it can last. So there's all kinds of variation. But when you're looking at the performance, you might be thinking about the startup phase or sort of the steady state phase. In the startup phase, that's where there's very few copies out, and you'd like to have the file be propagated very quickly. So that's just some that's the overview. So to wrap up this overview, I wrote an incomplete list of some performance issues peer-to-peer. One is the peer-to-peer peer selection strategies. How do the peers discover other peers, or if they have a list of other peers, how do they decide which peers to contact for pieces? Once you contact a peer, what pieces do you exchange? You could exchange piece lists. So one peer knows what the other peer has and could give pieces. There's push versus pull. One peer can kind of push pieces to another peer or can contact peers and ask for pieces. There could be heterogeneous link speeds, and peers with high access to the internet tend, like in BitTorrent, they end up tending to peer with other peers with similar link speeds. But there's effects of network topology and the spread of the geographic spread, and that gets influenced more with ISP-friendly operation. Without the ISP-friendly operation, the whole thing would kind of build up all over the world, sort of equal rate, but because of the ISP-friendly nature, it sort of does tend to spread. So you could see a file sort of spreading over to Europe, so maybe starting in Asia, and then it starts in the northeast of the US, and it kind of spreads, sort of like some infection or something like that. So the applications include file transfer, a lot of it like software, for example, live streaming, like the jet engine model I mentioned there, video on demand. In video on demand, there could be a lot of files out there that you'd like to maybe view, but be able to change channels. So you would like to have the early parts of these files widely distributed or cached, and then so that you could sort of start seeing anything quickly. And then if you stayed on something longer, then it could fill in, later parts. And this is a lot of the motivation for Laurent, I believe, at the Thompson Research Labs. Online interactive gaming or instruction, just some way to increase the bandwidth to lots of users. Any questions at this point? This is sort of ending the overview.
I think one of the question is missing. The behavior of selfish peer. I mean, peers which don't want to do anything, just want to catch.
Okay, yeah, so incentives for cooperation. That's one. Of course, in BitTorrent, you can't upload unless you download, because each peer has 4 neighbors, and they might give them a few files, but if they don't get pieces back, they'll drop them. That's a so-called tit-for-tat incentive mechanism. And before that, I mean, there's the idea of currency where you get some kind of points or something for uploading, and then you can spend those to download. And yeah, so incentives is many other issues. As I said, this is an incomplete list of performance issues. Okay. Okay. So I'll talk a bit about file exchange for a fixed peer population. And this pertains to the early portion of the flash crowd situation I talked about before. That's here. Maybe it's not that good of a model, but I'm thinking that there's, by some time, there's a lot of peers that are interested in a file, and this model assumes there's a fixed number of peers and one seed, and you want to get that file to this fixed number of peers as quickly as possible. Okay, so there's one file, so there's n peers out there, and the file consists of k pieces, and I'll measure the time in multiples of the time it takes to download one piece. Okay, so if the file is not split, the best completion time is k log 2 of n. Okay, this comes because it takes k time units for the seed to give the file to one other peer. So then 2 peers have the file. And then after k time units, 4 peers have the file. And then after k time units, 8 peers, and so forth. So it would take log 2 of n of those periods of length k for the whole file to get disseminated. So that would be k times log 2. If the file is split, then the best completion time is what? What?
Log 2 n plus k.
It's k plus, yeah, k plus log 2 of n, or vice versa. Because it would take k time units for the source just to get out the pieces. And then if each of those pieces was replicated in this doubling fashion, then the last piece would take log 2 of n more time to get disseminated to everywhere else. So that would be k plus log 2 of n. And that's optimal. And there's a nice paper of Richard Weber, I see him sitting over there, which gives a centralized algorithm for how would you schedule these pieces to do that. Okay. But if you don't have a centralized algorithm and you're sort of randomly contacting neighbors, the question is, can you do a similar completion time? So this is kind of related to the coupon collection problem. So if the contacts result in random pieces, it's kind of like a blind collection. You just go around and collect pieces without exchanging any piece information and just collect the pieces until you get a complete collection. Then it's the coupon collector problem. You've got k pieces you want to collect till you get the whole file. And we all know here that probably you get a complete collection after you receive k log k plus k times c coupons in the coupon collector problem is approximately the probability of getting a complete collection given you receive a Poisson number of coupons with the same mean. And then if that's true, then the number of coupons you receive of each type is also Poisson by the independent splitting property of Poisson random variables. So the probability you don't get a particular coupon is, let's see, what's this? To the k. Should be 1 minus here. This might be 1 minus. Yeah, to the k. No, maybe this is probably you don't get a coupon of a given type. So this is probably you do get a coupon of a given type. You raise that to the kth power. That's probably get all the coupons that you need. Anyway, it's like that. So, pardon? C is an arbitrary constant. So the idea is it's k log k, which is bigger than k. So you fix c, and so it's like a sharp bound. So k log k is how many coupons you need. And if you go up by c times k, so you just adjust it up and down a little bit, that sort of goes through the dynamic range of your success probability. So it's kind of a concentration type result. But it's very nice. It's k log k. But if you knew what you were going for, you just need k. pieces. The extra log k is because, well, it's really the mean number of pieces is one. It's a harmonic series. The first piece is useful to probability 1. The second piece is useful to probability k minus 1 over k. The third piece is useful to probably k minus 2 over k. And then the sum of 1 over those is k log k, roughly. So now if you use coding at the source coding, like digital fountain codes, then you take the k pieces and you transform those into coded pieces, where each coded piece is perhaps a linear combination of the original pieces. So you've got m, a larger number of coded pieces. And the idea is that the peers only need to collect k out of the m coded pieces, or maybe a few more than k. So then you don't have to fill in the complete collection. The hardest thing about collecting with random coupons is getting those last few coupons in. And if you've got this coding here, you just have to get enough. The idea of digital fountain codes from Luby, Chakralahi, Mitzenmacher is you just have a glass there, and you've got a fountain of digits coming, and just collect enough. And it doesn't matter which ones you collect. You just have to have enough, and then you can invert a matrix and recover your file. Okay, so that's nice. And then another step is to use network coding. And here each peer collects and produces coded pieces. So you've got k pieces, and then maybe a seed gives that pieces 2 plus 8 to a peer, and then later gives piece 1 plus 8 plus 7 to the peer. And then this peer could add these two pieces together using mod 2 addition, and then the 8s would cancel out, and it can produce piece 1, 2, 7. And send it to that peer, and then as peers get more pieces, every time they get pieces, they put it in their collection, and when they want to give someone else a piece, they take a random linear combination. Okay, and there's a paper of Deb, Medard, and Shute showing that you can achieve all-to-one dissemination in k plus log n time, the optimal time times the constant c, which is about, experimentally, it's a little bit more than 2, but maybe the proofs that come between 3 or 4, something like that. Without exchange of piece lists, you just send those pieces out. You don't have to say what pieces you have. So we were kind of intrigued by this. And we were wondering if you really need coding. What if you just send pieces at random? And, well, you get this coupon collector problem. But what if you also could poll pieces, and you're missing one piece, and you go around asking people, do you have piece 49? Okay, and maybe half the people should have piece 49 if they're not done yet. So we found out that just with a combination of push and poll, we got this. I wouldn't claim it works as well, but the theorems we have the same bounds, so it's the same C works. In fact, a lot of it's hard to prove things about network coding, and a lot of problems that don't involve network coding are really used to prove theorems about network coding. And so anyway, so that's sort of a result we had here. But then if you take protocols further, when you think about it, the amount of information you have to exchange a piece list is actually very small. In BitTorrent, for example, a file is broken into quarter megabyte files. This is 250 kilobytes, and into 200 pieces. So if you want to say what pieces you have, it's just a binary vector of length 200. Okay, so it's just 25 bytes, which is nothing compared to the large size of the files. So you could easily collect and update the collections of all your peers and the neighbors, all your neighbors and the neighbors of your neighbors and so forth. So it's not that difficult. So this is a result. I have a conjecture here. We haven't worked too much on this. And this is the case when there's n peers and n pieces. And the initial state is that each peer has one piece. And we use an exchange of piece lists. And it's a discrete time thing. So each peer is and for the protocol we use, each peer is an advocate for one piece. They want to see that piece get distributed. And we assume there's random contacts. And then when someone contacts, if peer 2 contacts peer 6, so the peers are going to be the rows here again, then if peer 2 already has piece 6, then the peer 2 gets a random piece. But otherwise, if peer 2 doesn't have peer 6 yet, since peer 6 is an advocate for piece 6, it makes sure that it gives priority to that piece. So if anyone contacts peer 6, it always gives out piece 6 first, and then something else. Okay, so actually, with this model, it's hard to tell if the peers are the rows and the pieces are the columns, or vice versa. It doesn't matter very much. Okay, there's a problem here. At this point, one peer had pieces 2, 3, and 6. Another peer had piece 2, 3, and 6. So if this peer contacts that peer, can't get anything useful. Okay, so that's why that peer only has 3 pieces and everyone else has 4 pieces. And at the end, it takes 1 extra. Okay, so we showed that this completes in time n plus O of log n. I think it's a pretty small constant. But we believe that the completion time is n plus 2 with high probability. Okay, this one, the scenario I just showed here was n plus 1. And it's because it's so unlikely that 2 peers have the same size collections. It's very unlikely that they're identical. So it's very unlikely that one peer can't help the other peer. But there's very subtle dependencies among the collections of the peers because they've been fraternizing with each other, exchanging these pieces. So we do like thinking about the sort of a matrix where you've got peers and pieces, and you're trying to fill in this matrix, and you can kind of look at the processes by rows and say how many pieces does each peer have, or you can say how many peers have a given piece. It's like looking at the columns. And I think it's interesting, but it's hard for us to really get I don't know if there's a really good handle on really sort of looking at both aspects at the same time. We can prove things, but every time we prove something, we're a little bit disappointed because we say, well, that worked that time, but we don't have some really general way to work with the rows and columns of these matrices at the same time. Okay, it's similar in that the one I showed you with like the jet things for the live streaming. There's rows and columns, and you can make independent assumptions, but they may not be true. We'll see a little bit more of that later. In fact, with this. So I want to move on to the third part, which is file exchange with continuous arrival of peers. And I'll start out with a model. It's largely in the paper of Masulier, Vojnovic, 07. I'm wondering if that date is right. Might be 06. Okay, this is the model. So I have a little diagram here. So the peers are coming in. And so this is the first model I talked about. I assumed that all the peers were already in the system. Here the peers are arriving continuously. So this could be after the big startup phase. So peers are coming, and when they get their collection, then they leave. And there's a seed that could give peers pieces. There might be an initial seeding, so when a peer starts downloading a file, it goes to some central website and gets one piece or some small number of pieces so that it has something to give away to other peers. So it starts somehow, it gets some pieces and starts uploading those to other peers and starts downloading. So I'm using the dark solid lines as the flow of the peers, and the dashed blue lines is the flow of the pieces. So I've got a loop here. It's like a queuing system of coupon collectors. They're all in there trying to get complete collections of coupons. They're trading with each other. And when they get a complete collection, then they leave. I also view this as a model for acquisition of knowledge by a community of monks or something like that. So I know there's some ancient religions where they want to memorize some holy book and they can't write it all down. So different people memorize different parts of the book. When somebody dies, you lose chapter 17. So you got to make sure that people, you have enough people sort of memorizing each piece. And as people get older, they know more of the book. But you lose someone that's got all that knowledge and they leave right away, it could lead to problems. Okay. So there's these K pieces, like chapters in a book or pieces of a file. Okay. So we let C be the set of strict subsets of this 1 to K. And then a peer that has a set of pieces C is called a type C peer. Okay? And a type C peer becomes a type C union I peer if it downloads piece I. It gets that one more piece. So the types of the peers are changing as they get more knowledge. And the downloads are modeled as being instantaneous. And a detailed Markov state would be X of C indexed by the set of subsets, proper subsets of 1 to K. Just keep track of the number of peers of type C. And exogenous arrivals come, and in the general model, we assume that the arrival of peers that have a collection C when they arrive is lambda C. That's the arrival rate. You could take special cases that lambda C is 0 unless C is the empty set, in which case all the peers arriving come with no pieces with them, and then they would rely on this fixed seed or the peers that are already in the system to give them pieces. Okay, we're going to assume random uniform contacts, which means that the peers contact other peers after some waiting time, and then they instantaneously download a piece. So offsetting this instantaneous download time is the fact that peers have to wait exponentially distributed period with parameter mu between the downloads, and those thinking times correspond to the download times, but then they make the model a lot simpler because we don't have to keep track of who's uploading or downloading or what happens if you complete your collection while you're uploading. Do you just leave then, or do you finish uploading to somebody else? So opportunities to upload or download from another peer occur at rate mu. Got cut off. There should be rate mu. Random useful piece selection. So once you've decided who you're going to get a piece from, you exchange a piece list, at least one direction, see what pieces you don't have that they have, and then a random piece from that set of useful pieces is exchanged. If there aren't any, then that exchange is just wasted, and then you have to wait another exponential amount of time with parameter mu to do it again. Sergey?
But why cannot you cannot take everything? You take only one.
Well, then that's like the first generation system, where you get the whole file at once. So, okay. So if we did that from the outset, I would have the whole file, and I contact you. I give you the whole file. That could take a long time. And then you give the whole file to somebody else. I give the whole file to somebody else. That's the so-called first generation system. So the second generation system is you pick up the pieces. So you could have some adaptive chunk size or something. And
so because of time, just
yeah, just because of time, because it's a trade-off. But this is the model, so whether the peers are operating in push mode or pull mode doesn't really matter in the mathematics, because each peer has these opportunities at sort of according to a Poisson process of rate mu, independently of how many peers are in the system. And you could think of they're waking up and pushing the people at that rate, or that they're pulling from that rate. It doesn't matter, because it scales up. The total rate of these transfers is, if there's n peers in the system, is n times mu. And so each uploading at rate mu and each downloading at rate mu. Okay, and the peers depart immediately upon completing a collection in this model. So you could write down a Q matrix for a Markov chain. So the rate going from x to x plus EC, this is a indicator vector of a type C with rate lambda C. This is new arrivals. Or you could have some peer that's a type C gets one piece and becomes C plus I. So then this x would increase by 1 in coordinate C plus I. this is if C is strictly, strictly smaller than k minus 1 pieces, so that when the new pair gets another piece, it doesn't leave right away. Otherwise,
the distribution of time in the system before you collect the full set. How long is the time in the system? Distribution.
Pardon?
Distribution of the time in the system before the team will collect the whole collection.
That's a good question. It's not part of the model. That's yeah.
Okay, but it's computer question.
That's a good question. It's a complicated question because these pairs. So the state, if there's k pieces, then the set of possible types is 2 to the k minus 1, and you can have lots of pairs could have different sets of pieces. It's like I said, it's like a matrix where you've got pairs on one side, and then the pieces on the other side, and you put a 1 or a 0. Which pair has which piece? And the number of pairs is variable also, so the number of rows would be varying. So it's quite difficult to calculate the distribution of the time in the system for that. Yeah.
The indicator of the complement is correct. Indicator of the complement of this.
Well, C here is a set of proper subsets. So this is just a way to say that C plus I is still a proper subset. Okay. So it goes down if a type C pair becomes a type C plus I pair, and then the coordinate C plus I will go up by 1. But if C plus I is a complete collection, then you just have 1 going down and nothing up. Okay, so it's a Markov model. So there's in this paper, it was 2006-8. Yeah, this was a Infocom paper, and then transactions on networking. They applied Kurtz's theorem on density-dependent jump Markov processes. They indexed the processes by n, parameter going to infinity. The arrival vector scaled up by a factor n, and in this model, there's no seed, no fixed seed. Okay, so that all the pieces are coming with the arrivals. And one model is one piece at the door. So you just get one piece when you enter, and it's a special case. And then you scale, and you take this state divided by n, and it converges uniformly in bounded intervals to ODE solution x satisfying x dot equals qx, sort of the fluid model. And then they analyze that. It's a symmetric system, right? The statistics are symmetric. And so it's a natural thing to analyze the symmetric, starting out with a symmetric state, like empty or something like that. And then it simplifies because you can just keep track of the number of pairs that have 8 pieces. And then you assume that all k choose 8 sets have equal possibilities. Okay, so that's what they did. So they analyzed the ODE for symmetric one-piece upon entry model. They identified the resting point, conjectured global asymptotic stability. And at the resting points, they found that the sojourn times, this is analyzing the ODE, or the resting point of the ODE. Let T1, T2, et cetera, be the how long the pairs spend in the different stages. So this is when they all come with one piece. So T1 is how long it takes them to get the second piece. T2, how long it takes them to get the third piece, and so forth. And they found these are increasing. They're increasing because the more pieces you have, the longer you have to wait to get additional pieces. But they're all less than 2 because under this model, almost half the people have each piece. So even if you're just missing one piece, when you make the random contact, you have a 50-50 chance that they're going to have the piece. So the time it takes to get that last piece should be 2 time units. Okay, so it's like that. And this refines an earlier 2-state model of Chu and Srikant, which had a 2-dimensional state space, which kind of assumed that everybody has, that the number of pieces they have is uniformly distributed between 1 and k, and then you just have a 1-parameter interaction, and you do a calculation saying, if I have a uniformly distributed number of pieces and you have, what's the probability I'm useful to you? Okay, and it'll be 1 given my size is bigger than your size, and even if my collection's smaller than your collection, I'm still probably very likely to have something to help you. And Yang and Devet-Xian had a similar two-dimensional model. So these models basically assume that these t's are all the same, and this Masulier-Vojinovic shows that it's actually a good approximation because these numbers just vary between 1 and 2. So that's good. So, and Xi was simulating this stuff. And we found that the stochastic packet level models showed poor performance. And so we're going to focus here on a similar scenario where the next slide shows simulations for no pieces upon entry but seed rate 1. And Illa Noros, are you here? He gave a talk here about a week or two before I came, and I just saw the slides of it. He made the same observations and some simulations there, and he wrote a paper. The paper uses the case k equal to 2, so that the file is broken into 2 pieces. But he made this observation that although things look really nice in that Masulier-Vojinovic paper, when you simulate it, it doesn't always work as guaranteed. So this is part B here, looking at the direct stochastic analysis that Xi and I did here. So this is our first simulations that Xi did. So here we've got pieces, we get peers coming in, and mu is the rate that they wake up and try to download, or the rate that they're requested to upload. And then there's a seed that doesn't scale. It's a rate 1, and at rate 1 it chooses one of the peers at random and uploads a random useful piece to that peer. Okay, so this mu part scales because it's which is 1. So if there's 100 pieces in there, the upload rate is 100 plus 1. Okay. That's as long as all the exchanges are useful. But if they start getting the same collection of pieces, then they're not useful. So this is a simulation. This is the number of peers in the system. And if the lambda is 0.8, and this is for a k equal to 40. So if it took 80 time units, upper bounding it to download, then 80 times 0.8 would be 64. So then you would expect by Little's law to have 64 peers in there on the average. And when lambda is 0.6, it looks stable. So this all looks nice. But then when lambda is 1.2 or 1.4, the number of peers just starts growing like that. Okay. So then we're wondering what's going on. And Illa talked about this 4 weeks ago here. So what is going on? What does that mean?
Ilka has this picture.
What?
Well, yes, it's up and down.
Okay.
Exchange.
Yeah, well, maybe with k equal to 2 something. I'm not sure. What happens is there's one piece that gets missing. In other words, symmetry gets broken. And it's easy to see starting out. If no one has anything, then somebody gets a piece. And, okay, everyone gets piece 2. Someone comes in, or some more peers come, and then the seed uploads piece 3, and they exchange. They all have pieces 2 and 3. It grows. And they might all have most of the same pieces, but they can't leave because the seed might not have even uploaded one of the pieces. And then when the seed uploads that piece, if it uploads it to someone that's already got all the other pieces, that peer leaves. It doesn't give that piece to other peers. So this is a simulation when lambda is 0.6, 1.4. Here, piece number 4. This is the number of peers holding piece number 4 on the average during the duration of the simulation. Okay, so and it's a symmetric model, so it was random. But this particular sample path, piece 4, was the rare piece. Okay, and so we have this theorem that in this case, so if lambda c is 0 when c is not the empty set. So peers don't come with pieces. So they all come at rate lambda with an empty set. So that means they're a type empty set. Then the process is positive recurrent if lambda is less than the seed rate, and transient if lambda is bigger than the seed rate. Okay, so this in this model again, there's a seed here. The peers are coming with no pieces, and I'd like to spend a few minutes talking about a proof here. So this is an if and only if result. So there's a positive part and negative part. I'll talk about the negative part first. It just follows the intuition I mentioned that you see in that slide, that you end up with one piece that's missing. So we select an initial state with many peers that are all in the 1 club. So 1 club means they have all the pieces except piece number 1. It could have been piece number 4, as I mentioned before, but since we get to choose the initial state, let's just suppose we've got a large number of peers that are all missing piece number 1. That's right here. And then we want to show with positive probability that the system just goes off to infinity. And this is assuming that the arrival rate of new peers is larger than the upload rate of the fixed seed. So we start at a point like that, and we just want to show that we go off like that. And we use a localization. So we assume that the process restarts if ever the fraction of peers in the 1 club falls less than 1 minus c, or c is some small number. So we kind of want to show that we stay in this corridor where the number of peers in the 1 club is always a high fraction. Okay. So I drew a picture here to show what's going on. This large bloated thing here is a 1 club, showing that most peers are in the 1 club. So the new peers come. We call them normal young peers if they don't have all of the other pieces yet. Okay. And they don't have piece 1 either if they're normal. And what usually happens is they're in here, and then all those 1 club peers are doing contacts. So each of these peers gets contacted at rate mu, and most of the contacts come from the 1 club. So they get all the other pieces except piece 1 from these 1 club members. So there's this population here that has all that knowledge except piece 1. So they go up there normally. But the seed might infect one of these, and if the seed contacts one of these, it might give them piece 1. Okay, then that normal young peer becomes infected. They've got the missing piece. And then they go over to this box, and they can give other pieces to the other infected peers, but here they can give that piece to the 1 club members, and then the 1 club members can depart. Okay? And the seed can also cause the 1 club members to depart. And the infected young peers can infect other young peers with that forbidden knowledge, like that secret knowledge. Okay? But what we want to show is that it's like a branching process here. When these infected young peers contact another peer, most peers are in the 1 club. So mostly they're just going to be contacting other peers in the 1 club. And so the idea is it's a highly subcritical branching process, and it dies out fairly quickly. And so this stuff down here, the idea is to show that that's not important. And so the main trajectory is the peers come here, and they go into the 1 club. And the main way they get out is that the seed is getting them out at rate u sub s, which does not scale. So if lambda is bigger than u sub s, the 1 club just gets bigger and bigger, and it just goes off to infinity. Okay. So we did a proof of that. So one part is that if you look at the total number of young peers, it's stochastically bounded by an MGI infinity queuing system because they've got to get their k pieces, or k minus 1 pieces, to get out of here, and they're getting them at rate mu times 1 minus c, because the 1 minus c is the fraction of peers in that 1 club, and they just have to get downloads from that 1 club to get old. I mean, not be a young peer anymore, and move into the 1 club, or if they happen to get infected, then to leave the system. Okay, so if a seed creates a new infected peer, that peer can infect other peers, and the sum of the times the infected peers are in the system is stochastically smaller than a busy period of an MGI1 system the busy periods of queuing systems have a branching process analysis, and the sum of the times in the system during a busy period is exactly the sum of the times of how long these the infected a root infected peer is, and then how many other infected peers get infected, sort of how long they're going to be in the system infecting one club peers. And so you can bound that mean and then basically show that the mean number of peers that get kicked out of the one club due to one infected peer being infected by the seed has a bounded mean and variance. And then the arrival rate of infected peers caused by the seed is also small. And so basically what I said before works. You can just sort of ignore this bottom part. So that's for the positive part. And then G said, okay, let's prove the negative part. And I said, oh, gosh, we've got all these interactions in this matrix. How are we going to do that? And we only know one technique for proving negative or positive results. What's that?
Foster criteria?
Yeah. Hmm?
Foster criteria?
Foster criteria. You got to find a Lyapunov function. So, quadratic. Yeah. So at least we can try a quadratic Lyapunov function with Foster's criteria. It works. And not only that, we don't have to keep track of the detailed state, but we just need to keep track of how many peers have I pieces for each value of I. And that works. We're a little surprised, at least I was, maybe G wasn't surprised, but I was surprised. So there's like two cases to think about. One is if all the peers have the same number of pieces, they all have I pieces. That's a bad state potentially because they could have the same set of pieces and they couldn't help each other. But here we're assuming that the arrival rate of new peers is less than U sub S. So the fixed seed would be getting peers out of this state faster than new peers are arriving and could be getting into this state. Okay. On the other hand, if the peers are not all have the same number of pieces, so some peers have I pieces and other peers have J pieces, then all of these peers with J pieces can help all of these peers with I pieces. So you could have a high exchange rate there. Okay. And basically, like by looking at these two pieces, you could show that a Lyapunov function C sub I times the number of peers with I or fewer pieces squared, should be a square there, quadratic, is a Lyapunov function. And you can show that the drift of this is less than epsilon times the number of peers in the system. Just by looking at these two cases, you can figure that out. So basically, that's it. That proof works. And so the one club problem shows up as additional rest. So this is a stochastic analysis, which was not detected in the fluid model. And I think it was not detected not because the fluid model can't detect this, but because they only looked at symmetric starting points. So if you see the one club intuition that you can get from simulation and then go back to the ODE and start with the initial point being asymmetric with a lot of fluid in the one club state, then you'll see that here. So the one club problem shows up as additional rest points, the ODE, but non-symmetric states must be considered even if the model is symmetric. So take the initial state corresponding to a large one club. This model is a little bit different than in their paper. In their paper, they assume that each peer comes with one piece chosen uniformly at random. And that one's right on the cutting edge. The seed rate is sort of proportional to the number of peers. It's almost like U sub S equal to 1 in the previous model. And G has a poster on Thursday explaining how if you let mu go to infinity, you come up with something that's null recurrent, just on the borderline between being positive recurrent and transient. Okay. I'll just close with this last slide. There's 3 mechanisms that are implemented or commonly discussed to enhance peer-to-peer systems. One is rarest piece first selection, rather than random useful, and Ilya talked about that also. I think he talked about contacting 3 peers, seeing which piece is underrepresented, and then downloading a piece that's underrepresented. And BitTorrent also goes for rare pieces. Second is network coding, where peers in the seed exchange linear combinations of packets. And the third is that some peers remain in the system for some time after completing a collection. They're sort of generous to stay behind. So which ones of these defeat the one club? We call it the missing piece syndrome, or the one club problem. The third one? Third one, definitely. If a peer remains in the system for some time after completing a collection, this is against early retirement. Then you can keep on uploading those pieces even after you have a complete collection. How about rarest piece first selection? What if you get stuck in that state where you've got a large number of peers that all have all the pieces except for piece 1? In our model, we're assuming that anytime anyone can, they'll always get piece 1. Piece 1 is a rare piece, and there's definitely a priority on it, and it doesn't help. It's still the same problem. Although, it's probably a lot lower probability. If you do simulations, you might not even find that it's a problem. But at least in theory, you still have a problem. And network coding, it depends on the formulation. In some versions of this, like the one I talked about, it's still a problem even with network coding. And if you're sort of missing in one dimension, and it just takes one last piece to come in, then the peers would, this is in the case where there's a seed. So suppose everyone has their codimension 1. They're all missing one dimension. And there's a seed that can give you a random linear combination. Every time someone gets that random linear combination from the seed, they depart. But if the total arrival rate is larger than the seed rate, you'll be building up this one-dimension club where they're missing one dimension faster than the seed can knock them out. Okay? But if you take the Masuliev-Vojinovic model where the peers come with a random linear combination, then each new peer is basically infected because each new peer could complete the collection of any other peer, and then you don't have a problem. So it kind of depends on which model you're talking about to see whether network coding doesn't work. So that's what I want to talk about. I mentioned the references here. So what? The third one for sure, and the second one for the first model I talked about, it would not help. But for the Masuliev model, if you come with one random piece upon arrival, it would help because you wouldn't get stuck that way.
First one is open.
Yeah. Pardon?
The first one is open.
No, the rarest piece does not work. It's not open. It does not work. Rarest piece first does not eliminate the missing piece syndrome. Because if you get into a state, which could happen by the randomness of arrivals, where there's a large number of people that all have all the pieces except for piece 1, then piece 1 is rare, and they're all going to be going after the rare piece. But if a peer leaves when it gets that rare piece, and if lambda is larger than US is the only way they can get the rare piece, is from the fixed seed, then it will be unstable.
So there is a proof of this? What do you want? Or is intuition behind?
Well, I just gave the proof.
No. So you formulated this as an open question.
It's not an open question. It's a closed question. Okay, I was posing it as a rhetorical type question for the presentation. I wasn't posing it as an open question for you to work on for the next month. Okay, because it comes from the proof, and the proof of the negative part, we're assuming every time the seed contacts anybody, it always uploads piece 1. That would be, because it's hard to analyze it any other way. And so it basically is giving, already we're assuming that priority is given to the rare piece, and it's still unstable if lambda is larger than US. So yeah, those are references. There's this Neuros paper that was talked about here on the stability of a 2-chunk file sharing system. Thank you.
What a great lecture. Brilliant timing, and including the questions as well. We've got time for some questions or comments. Please.
Can I have 2 questions, please? The first question is about the third solution when you allow complete user to remain in the network for some time to become sick. So in this case, if you increase the rising intensity, then I'm sure that there would be some threshold that if you go beyond this limit, then the system will become unstable. So in this case, what is the reason for the unstability? Does it come from the rare path phenomenon or for some other reason?
I've written down a condition. If you assume that the pairs stay for exponentially distributed amount of time with parameter gamma after they leave, then basically 1 over gamma or mu over gamma is the expected number of pieces they upload when they're there. So if that's 1 or more, then it would become stable. Or if it's less than 1, then that plus use of S, some linear combination, you can write down the condition. So they do have to stay long enough. If they just stay, but basically if they stay long enough to upload 1 piece. Intuitively, I think you could even match that to say the pairs aren't useful until they get 1 piece. So there's some time there they're not doing anything. So to make up for it, they have to stay 1 unit of time, enough to upload 1 piece, and that seems to be just enough to make it stable. So if anyone just stays for 1 year after retirement, or before they would retire, to upload 1 last chapter, then it would be stable.
Very relevant for me because I thought I was retiring from another job 2 or 3 years ago. It's called double dipping, actually, and it's a good thing. Yeah, other questions? I mean, I wonder if I could make a comment. I mean, it's a fascinating talk for me to see how you can get really quite subtle and not intuitively obvious dynamics out of these stochastic systems. And we did have a fantastic example of this as well a couple of years ago when a guy gave a talk about futures trading. Yeah? In futures trading, you take one of the futures that you're talking about, you have a stack of bids and a stack of offers, and it's trading, it's event-driven on the millisecond time scale. And the example that he showed, and this is probably easy for you guys to explain, the example he showed was when a trader, without realizing it, brought a new system in which had delay built into the router. The delay in their system, in their router, drove the system into 5 seconds of instability, in which, because of the delay, they were buying high and selling low. They lost $150 million in 5 seconds and then pulled the plug. So I think there's a real future if you guys can understand and counter that system. But I think it's just a great talk, Bruce, and thank you very, very much for the sharing.